SDAccel provides the user with an easy-to-use environment, where the user is not only guided to create and optimize different kernels that will be executed on the FPGA device, but since the steps to generate the bitstreams are many and time-consuming, this framework provides the user with the different emulations that help the designer in testing the correctness of the produced kernels at different levels. We are back to a quite well-known picture showing the SDAccel design flow. As we know, this picture provides a very high-level overview of the steps to generate a functional hardware design by means of a bitstream that will have to be downloaded on the FPGA and a host binary that will be linked with the OpenCL runtime libraries to manage the communication with our device. All these steps start with a high-level description of our kernel file, and to start the flow we need also to define a host code. This file needs to be in C, C++ or OpenCL, as it will exploit the APIs provided by the OpenCL language, while our kernels can be described using C, C++, OpenCL, or RTL. As a reminder, even if the designer decides to describe the kernel function using Verilog or VHDL, the code still needs to be compliant with the OpenCL memory and computational model. Okay, now that we have the kernel and host file, we can either use a makefile or the graphical user interface to design the kernel and to optimize it. In these regards, the framework provides multiple directives that help with this process. Once we have a first implementation of this kernel, SDAccel provides us with two different emulations that are used to check the functionality of our code at different levels. In particular, we can perform a software and a hardware emulation. The software emulation is the fastest simulation and has its main goal to ensure the functional correctness of the code we are trying to accelerate. Usually, this emulation is used in an iterative process in the first step of the design of the kernel and helps the designer in creating multiple kernels while ensuring that each kernel is performing its specific task correctly. At this point of the development, performance is not the main goal. During this emulation, both the host and the kernel code are compiled to run on an x86 processor and are executed as a normal program. While this first emulation ensures the functional correctness of the kernel codes we are providing, it does not ensure correctness of the FPGA execution target. SDAccel generates at least one compute unit for each kernel provided, meaning that it's necessary for the application designer to check that each compute unit that is being implemented is producing the correct results. During this step, the logic circuit is generated, and then SDAccel invokes the hardware simulation available within the framework to test the overall functionality of the implemented logic. Notice that the hardware emulation does not guarantee that our final bitstream will be implemented, nor that it will produce correct results once it is downloaded on our FPGA device. However, it's a necessary step, as well as a first step to validate our design. If from the one hand the software emulation is as fast as compiling a C, C++ program for our personal computing, the hardware emulation can take much longer. It's suggested, in fact, that to perform hardware emulation using a small, still significant dataset, as it may take up to some hours if a huge dataset is provided to the emulator. After the hardware emulation is performed, it is also possible to analyze the results by looking at the waveform. In this way, the designer is capable of checking all the signals and their behavior during the simulation. Furthermore, analyzing the waveform, the designer will also be able to obtain some performance estimation of all the analyzed kernels. Hardware emulation is the only emulation that is available with all the three kernel specifications: C, C++, OpenCL, and RTL. The same story does not apply for the software one. Within this context, we can easily understand that if we provide an RTL code to SDAccel, the framework will not be able to perform a software emulation, as a hardware description is provided. Once both the simulations have been performed, it is possible to start building the final application by generating the final bitstream and host binaries. This is the longest process of the flow and can take from some hours to days of computation. Finally, once the binaries have been generated, it will be possible to perform the final benchmarks directly on the FPGA device.